Over the next couple of videos, we'll be studying one-dimensional kinematics. We'll explore what kinematics is. We'll look at position, velocity, and acceleration time graphs. We're going to derive the one-dimensional equations of kinematics, and these are where Vfx is the final velocity of a particle, Vxi is the initial velocity of a particle, Ax is the constant acceleration of that particle over time t. And we're going to see how to apply these equations to real-life problems, including freely falling objects. And at the end of each video, we're going to have a look at some example problems to solidify our knowledge. So, kinematics is a branch of physics that deals with motion of objects without considering the forces that cause the motion. And one-dimensional kinematics focuses on an object's position, displacement, velocity and acceleration along a straight line. And this straight line can be the x-axis. In one-dimensional kinematics, acceleration is constant throughout time. So if I draw an acceleration time graph here, where we got acceleration on the y-axis and time on the x-axis, acceleration will not change for a particular particle moving in one dimension. So what's this mean? Well, imagine you're on an aircraft and you're just about to take off. As the plane accelerates on the runway and takes off, the force you feel on your back as you're sitting down on your seat will remain constant. It won't change over time. Physics categorizes motion into three main types. We've got translational motion, rotational motion, and vibrational motion. In one-dimensional kinematics, we simply focus on translational motion in one dimension, and we normally choose the x-axis for this dimension. In later lessons, when we talk about gas pressure, we can describe the gas molecules within a container with translational motion. We can ignore their vibrational and rotational component, and we can derive the gas laws simply by focusing on their translational motion in 3D space. So in part one of this lesson, we're going to look at three important quantities in kinematics. That is position, velocity, and speed. Now, in one-dimensional kinematics, a particle's position is the location of a particle with respect to a chosen reference point. So let's draw a one-dimensional line here, and our reference point is the front door of our house. Everything to the right of our house has a positive value, positive x value. And everything to the left of our house has a negative x value. Now the particle in this situation is going to be represented by a bicycle. More specifically, the front handlebars of the bicycle here. Now, as I move up and down my road, I want to record my position every 10 seconds. And the position that we record is relative to our reference point here, the front door of our house. So, for example, if I decide to go to the store and buy some bread, I would need to move in the positive X direction. And what we'll do is we'll plot my journey in a minute in a position time graph. So let's say I've got a neighbour over here that needs help getting her shopping in. So before I go to the store, I decide to go in the negative X direction and help her take in her shopping. And remember, we're recording our position every 10 seconds. So what would this look like on a position time graph? Now, before I go any further, this positive X direction, or the direction we decide the positive X direction should be, is our choice. We could quite equally choose this direction, the left-hand side, to be the positive X direction. So at the bottom here, we've drawn a position time graph of our activity. And the green dots on this graph, which you can just about see, are our locations at the 10-second mark. So initially, on our bike, we head to the left-hand side, and in the first 10 seconds, we are at -5 meters. In the next 10 seconds, we are at -20 meters. And then we spend 30 seconds helping our neighbour in with her shopping. And then we head in the opposite direction until we reach the store, which is in the positive 20-meter location. We spend 10, 20, 30, 40, 50, 60 seconds there, so 1 minute, and then we head back home, which is at 0 meters, our point of reference. So what can we tell from this graph? Well, first of all, because we're plotting our position every 10 seconds, this blue line here is an estimate. So we don't know what has happened in between these 10-second time intervals. Say, for example, I'm going towards the left to help out my neighbour, and I'm in between 10 and 20 seconds. If I drop my wallet, for example, at 15 seconds, I might stop for a couple of seconds and then continue on. This blue line here gives no indication of the exact position I was in between these 10-second intervals. Now, a very important definition you need to be aware of is displacement. The displacement of a particle is defined as its change in position in some time interval. So we know what our time interval is, which is 10 seconds. The displacement is represented by a delta x, which is equal to our final position of our particle minus our initial position. Now, from this displacement, we can have a negative or a positive result. And our displacement here is a vector quantity. So let's say we're looking at the first 10 seconds. What is our displacement over that time period? Well, our final position, so if I write this out, our delta x is equal to our final position, which is -5, minus our initial position, which was 0. So our displacement is -5 meters. But if we have a look at the time between 60 seconds and 70 seconds here, our delta x becomes our final position, which is 10 meters here, minus our initial position at 60 seconds, which was -10. So our displacement is +20. Now you can see here that when we have a positive displacement, our gradient is positive. And when it's negative, the gradient is negative. But the gradient, which we'll talk about in a minute, also gives us our speed and velocity. Now we'll cover vectors properly in the next section, but vectors have both a magnitude, which is this value here, and a direction, which is represented by the sign. Now if we go back up to our diagram at the top here, we can see that direction is depicted by the direction of our values on our x-axis. But there's a very important distinction that we need to make between displacement and distance travelled. These two quantities are not the same thing. Displacement is a vector quantity, and distance travelled is a scalar. Now, distance is the length of the path travelled, irrespective of the direction. So if we take my journey, for example, we know that we travelled 20 meters towards the left-hand side, then we travelled 40 meters towards the right-hand side, then we travelled 20 meters again towards the left. So that's a total of 80 meters. That's the distance travelled. So we got 20 plus 40 plus 20 equals 80, and that's the distance travelled. But the displacement over the entire journey is 0. And we can see this from this equation here. So my initial position at 0 seconds is 0 meters. So delta x is equal to xi, which is the initial position, which is 0. But my final position is also 0. So we've got 0 minus 0, which is 0. And that's my displacement over the entire journey. So you can see that the distance travelled and the displacement can result in two separate values. And this will become more important later. With our position time graph, we can also work out our average velocity during two different time intervals. So our average velocity is represented with this equation. So we got the average velocity along the x-axis is equal to our displacement along the x-axis over delta t, which may be 10 seconds, so in between two adjacent plot points, or it could be between any two plot points on this position time graph. So for our first 10 seconds, we can work out our average velocity. In the first 10 seconds, our final position is -5. So -5 minus our initial position, which is 0, divided by the difference in time, which is 10 seconds. So we got a value of -5 over 10, which is equal to -1 over 2 meters per second. So we can see here that the average velocity is also a vector value because it depends on the sign here and on the direction of the gradient. So in between 10 seconds and 20 seconds, we've got a steeper gradient. So that suggests that our average velocity is going to be higher. It's going to be a larger magnitude. Let's work this out. So average velocity between 10 seconds and 20 seconds, we've got a final position of -20, -20, an initial position of -5, and again that's divided by 10 seconds because we're only looking at the difference between 10 seconds and 20 seconds. So what do we have? We've got -20, and because we've got two negatives here, that turns into a positive. So we've got -15 over 10 equals 1.5 negative meters per second. So you can see that the magnitude is greater, but we've still got the same sign. And we've got the same sign because the gradient is still moving in the same direction. But we've got a larger magnitude, which means that we were moving faster between 10 seconds and 20 seconds than we were moving between 0 and 10 seconds. So we sped up in the negative x direction as we were moving towards our neighbour. Now our gradient is flat here, which means that our velocity was 0. When we get to this side here, our gradient flips in the opposite direction. Our gradient is now positive, which means our velocity is also positive. And the steepness of the gradient is the magnitude of our velocity, or in other words, our speed. So if I draw a positive gradient here now, between two plot points that are 10 seconds apart, on the x-axis here is the time, so that's delta t, and this value here, this length here, represents our delta x, which is equal to x final minus x initial. Now, our average velocity over the entire time period of my journey is going to be 0. And that's because our displacement during those 160 seconds is 0. So our velocity during the entire time is the final position, which is 0, because it's 0 on the x-axis, minus the initial position, which is 0, divided by 160, which equals 0. But our average velocity is not the same as speed. Speed is a scalar quantity, and the average speed is the total distance travelled divided by the total time interval required to travel that distance. So we worked out our distance travelled previously, and we worked that out to be 80 meters, because we moved 20 meters in the negative x direction, and then we moved 40 meters again in the positive x direction, and then 20 meters in the negative x direction. And that adds to 80 meters. And we did that in 160 seconds. This means that our average speed is 0.5 meters per second. Now this can be counterintuitive at first, but the reason why our average velocity is 0 is because the velocity is a vector quantity, and it takes into account what direction you're going. We moved equally into the negative direction as we did into the positive direction, so it cancels out. The first question is asking us the position versus time for a certain particle moving along the x-axis is shown in figure 2.3. Now this graph here is taken from Physics for Scientists and Engineers by Surway and Jewett. And this was my undergraduate physics book. But it wants us to find the average velocity in these time intervals. Now in the previous lesson, we learnt that the average velocity of a particle during some time interval is the displacement delta x. So the displacement x divided by the time interval delta t, during which that displacement occurs. So if we write this out, the average velocity along the x-axis is equal to the displacement along that x-axis over a specified time interval. So we got our time intervals up here. So our delta t for the first one is 2 seconds. Delta t for the second one is equal to 2 seconds. And the delta t for the third part of the question is 8 seconds. And all we need to do now is to read off our final positions and our initial positions from the graph at these specific times. So let's do that. So part A, delta V x is equal to the final position, which is 10 meters, minus the initial position, which is 0 meters, divided by 2 seconds. And we get 5 meters per second. And because average velocity is a vector quantity, the sign is important here. So positive signifies a gradient that increases over time. Part B, we got a slightly different situation. We got the same time interval, but we have a negative gradient where the gradient decreases over time. And that suggests that the particle is moving in the negative x direction over that time period. So we've still got a delta t of 2, but our final position is smaller than our initial position up here. So our final position is 5 minus initial position 10, and this equals minus 5 over 2, or minus 2.5 meters per second. And you'll notice that because the magnitude is smaller, the gradient is less steep than part A of the question. So we've got a steeper gradient from 0 to 2 seconds and a more shallow gradient from 2 to 4 seconds. And the particle's direction has flipped. So lastly, part C of the problem. Our average velocity is equal to our final position, which is 0, minus the initial position, which is 0, divided by 8 seconds. Now this equals 0. And again, as I explained in the previous lesson, the average velocity is not the same as the average speed. Average speed is equal to the total distance travelled divided by the total time. And this is a scalar quantity. It's not dependent on the sign or the direction of the particle. So if I were to work out the average speed for part C over the 8 seconds, I would have to add up the total distance that the particle travelled in that 8 seconds. So in the first 2 seconds, it travelled 10 meters up here, 10, plus, then it moved in the negative x direction by 5, but because the sign doesn't matter. We just simply add that distance. Then we're not moving at all. Then we go from +5 to -5, and the difference there is 10 meters. So we add a 10, and then we move in the positive x direction by a distance of +5. So our total distance over the 8 seconds is 20, 30. And that's 30 over 8. And the average speed is 3.75 meters per second. A particle moves according to the equation x equals 10t squared, where x is in meters and t in seconds. Find the average velocity for the time interval from 2 seconds to 3 seconds. Now this question is actually a lot easier than it looks. We have a quadratic equation here, and this is not necessary to answer the question, but we could draw a graph of this polynomial equation here, where x would be on the vertical axis and on the horizontal axis would have time in seconds. And this would create a line that looks something like this. Now we'll see this type of position time graph in future questions. But this is the type of motion a particle would take when the acceleration is constant. So if you think of a freely falling object, if you drop a coin from the top of the Empire State Building, for example, the coin initially would have a low velocity, which is signified by the low gradient here, because the gradient on a position time graph is the velocity of this particular particle. But as time goes on, the coin will pick up speed, so the gradient would increase. But if we get back to the question, we've got a particle that moves according to this equation. All we need to do is create a table of values for t and x. So if I have time on the top here in seconds, we're interested in 2 seconds and 3 seconds, and this is our table here. But we're also interested in the value of x, and the position of our particle is dictated by this equation here. So we can plug in the values of time into this equation to find the value of x. So 2 squared is 4, times 10 is 40. So we got a position of 40 meters at 2 seconds. At 3 seconds, 3 squared is 9, times 10 is 90. So at 3 seconds, we've got 90 meters. So the average velocity, again, is shown by this equation, which is the displacement over the change in time. So our final value at 3 seconds is 90 meters. That's but our initial position is 40 meters. So we minus by 40. And our time difference between these two distances is 1 second. This is equal to 50 divided by 1. Or in other words, our average velocity is 50 meters per second in the positive x direction. Okay, so third and final question. A person walks at a constant speed of 5 meters per second along a straight line from point A to point B, and then back along the line from B to A at a constant speed of 3 meters per second. What is there, A, average speed over the entire trip, and B, average velocity over the entire trip. So this question is actually quite tricky, and we're going to need to take this step by step. So we have a one-dimensional line with the first point being A and the second point being B. But we don't know the distance between point A and point B. So at the moment, the best we can do is assign it a variable, and we'll call that variable D. We do know though that we're moving from A to B at 5 meters per second. So we have a velocity and a direction. And we're moving backwards from B to A at a slower pace of 3 meters per second. So because our speeds between these 2 points are different, we can assume that the time it takes to get from point A to point B is different to getting from point B back to point A. So we've got 2 different times here. And again, we don't know the times, not yet. So let's say that moving from A to B at 5 meters per second is represented by a t with a subscript of 1. So that's moving from A to B. Moving from B back to A has a time, let's say, of t2. Now t1 and t2, they're not equal to one another. We can see this because our speeds are different. Our t1 going from A to B is going to be shorter than going from B to A because we're moving faster going in this direction. But we do know what our average velocity is. In the previous lesson, we learnt that an average velocity along a straight line is the displacement over the change in time. So let's assume for a second that this line lies across an x-axis and our positive direction moves from A to B. Now this is our choice. We could quite easily say that moving from B to A moves in the positive x direction. But I'm assuming here that the position at point A has a lower x value than the position at point B. So we've assigned this direction as our positive x direction. Now our velocity here is a vector, so it has a direction. And in one dimension, our direction is signified by a positive or negative value. A person walks at a constant speed of 5 meters per second between A and B. Their velocity is positive 5 because we've assigned this direction to be a positive x value. So that's what we'll do here. So we've got a positive 5.00 meters per second is equal to some distance we don't know yet, which we've assigned with the variable d. I'm going to write d down here, over a change in time, which we've called t1. So we're going to put t1 there. But we also know that we're moving in the negative direction at minus 3 meters per second. So we can write another equation with our average velocity here, using this equation here. We know that we're moving in the negative direction at 3 meters per second at the same distance d over a new time period, because it will take longer to get back from B to A at time t2. So what can we do with these two equations? Well, because we want to find our average speed over the entire trip, not just from A to B or B to A, but from A to B to B to A, we can add these two equations together. And what's this look like? So effectively, what we're saying is we want the average velocity over the entire trip. That will be part B of the question, but it also works for speed here, which is the total distance over the total time. And this total distance is 2d, or d plus d. D plus d over the total time, which is t1 plus t2. And t1 here, if we transpose this equation, we can make t1 the subject. So t1 is equal to d over plus 5 meters per second. t2 is equal to d over minus 3 meters per second. We can ignore the negative sign because we're only interested in the speed, and speed is a scalar. Now at the bottom here, we've got a fraction that we need to add together. So we need to simplify this denominator first to make our lives a bit easier. So when we're adding fractions together, we need to find the lowest common multiple of these two numbers, 5 and 3. So if we multiply out 3 and 5, 3, 6, 9, 12, 15, and 5, 10, 15, this is the lowest common multiple, because these two values can divide evenly into this number without leaving a remainder. So we have 3d at the top with 15 at the bottom, and all we've done here is multiplied this fraction by a value of 3 to ensure that the denominator here equals 15. Likewise, we're going to have to multiply this fraction here by a value of 5 to ensure that this denominator at the bottom here equates to 15, but the numerator at the top will equal 5. So we've got plus 5d here equals 15. And now we can add these two fractions together quite easily, just by adding the components at the top here. So we have 8d over 15. And with this, we can multiply by the reciprocal when we're dividing twice like this. So what we have here is 2d divided by 8d over 15. And if we take the reciprocal, we can do 2d multiplied by 15 over 8d. The d's cancel out, leaving us with 2 times 15 divided by 8, which is equal to 3.75 meters per second. And just to note here, this should not be a vector, it's a scalar. This is the speed rather than the velocity. Okay, so what about the average velocity over the entire trip? Well, this is actually counterintuitive, but the average velocity is 0. And that's because the person starts and ends at the same place along this straight line. So if you remember, this is the average velocity, or this equation gives us the average velocity, which is a vector. Our average velocity is equal to our final position, which is A, and let's assume A is at 0, minus our initial position, which is also A. so minus 0, and we divide that by the time. We don't know the time, but that doesn't matter because we have a 0 in the numerator. So we've got a value of 0 meters per second. In the previous video, we looked at how to calculate the average velocity and the average speed over a specified time period. And that's delta x over delta t. But what this can't do for us is tell us the instantaneous velocity and speed at any point in time while the particle is in motion. So this equation here cannot tell us what the speed might be or the velocity might be at this location here. And when we're measuring the motion of a particle throughout time, we're doing so at fixed time intervals. So here we're doing it every 10 seconds. With the instantaneous velocity, we can measure the velocity and speed from a position time graph at any point in time. So if I wanted to calculate the average velocity between times A and B, I would draw a straight line connecting these 2 points. And this gradient here will represent the average velocity between points A and B. But you notice that this isn't actually all that precise, because close to point A, we've got a steeper gradient here, so the velocity is going to be greater. And likewise, close to point B, we've got a shallower gradient, so our velocity is going to be less than the average velocity. But let's imagine for a moment that we shrink the values of delta x and delta t. So instead of measuring the average velocity between A and B, we measure the average velocity between A and a position between A and B. So something like this. So this point here. So you can see that our new value of x here is smaller than the original value of delta x here. So we've got a smaller value of delta x and a smaller value of delta t. And you can see that this gradient is steeper, which means that the average velocity between these two time periods, between A and B prime here, is greater. But if we continue to shrink delta t and delta x smaller and smaller until those values approach 0 or delta t approaches 0, then we've got a gradient that is more representative of the velocity at point A. So how can we actually write this down mathematically? As delta t approaches 0, we'll have something that looks like this. So the velocity along the x-axis equals the limiting value as delta t approaches 0 of the ratio of delta x over delta t. And what we find when we shrink our triangle here so that delta t shrinks down and approaches 0, it never gets to 0, but it approaches 0, then we have a situation where our gradient at any point along this curve here is a tangent to the curve, which means the straight line is at a 90-degree angle. And no matter where we are on this line, our tangent will always be the gradient of that point on the line, which will give us the instantaneous velocity. So at the moment, this curve here is an estimate of where the particle will be between our clock ticks here. But this curve can be represented by an equation. And for those that have studied calculus, you'll know that you can work out the gradient of a curve by using differentiation. So this curve here might have the form of something along the lines of the final position of the particle, which we'll represent by x lower script f, will equal the initial position of the particle plus its initial velocity multiplied by the time plus half the acceleration of the particle by t squared. Now we'll get into this equation at a later lesson, but what we can do with this equation is we can differentiate with respect to time to find the gradient at any point along this curve. And this dx over dt is the instantaneous velocity because it's the gradient. So let's put this into context a bit. We could have an equation, we could have a curve that's represented by an equation that looks like this. And 3 here is related to the acceleration. And if you studied dimensional analysis in a previous lesson, you'd realize that an equation, their dimensions or units have to balance each side of the equation. So we've got a length on this side, which is equal to a time squared, but we've also got an acceleration, which is a length over a time squared. The times will cancel out, leaving us with a length on this side and a length on this side, so they balance. So this 3 here must be an acceleration or have units of length over time squared. So we can also represent our instantaneous velocity here by saying delta x over delta t. And again, this value is a vector. And we can see it's a vector because the gradient, which represents our instantaneous velocity, can be positive, as it is here. We can also have a negative instantaneous velocity, which will be, for example, here, where the gradient slopes down. But we can also have a velocity that is 0. And where do you think on this graph the velocity would equal 0? Well, the velocity will equal 0 when there is no change in position over a specified time period. In other words, when the gradient is 0. So if we imagine that this curve represents the position of an electron within an electric field. At 0 seconds, the electron is moving in the positive x direction. Then it might experience a negative electric force, which slows down its motion at a constant acceleration until it stops moving. Then because you have a constant acceleration in the negative x direction, so the electron, as it's moving upwards, it's being pushed down by a negative electric field. Because we've got an acceleration in the negative x direction, then the electron is going to continue moving down until it reaches F. And there's some other electric field that may be influencing its position at this location in the x direction. We also have the definition instantaneous speed. Which is defined as the magnitude of the instantaneous velocity. So this is different from the average velocity and the average speed. In previous lessons, we showed that the average velocity is not necessarily the same as the average speed. But for instantaneous velocity and instantaneous speed, Their magnitude is the same, but the only difference with the instantaneous speed is that it's a scalar quantity, which means that it doesn't have a sign, but a vector does. A particle moves along the x-axis. Its position varies with time according to this expression, where x equals minus 4t plus 2t squared. X is in meters and t in seconds. Use the figure and expression to A, find the average velocity between the times t equals 1 seconds and t equals 3 seconds, and B, find the instantaneous velocity at t equals 2.5 seconds. So I have mentioned in previous lessons that the average velocity is equal to the final position minus the initial position over some length of time, delta t. So our particle's motion is explained with the blue curve here, which relates to this expression, x equals minus 4t plus 2t squared. So our final position of our particle at t equals 3 seconds is 6 meters. But our initial position at 1 second is minus 2 meters. And that's over 2 seconds. So this equals 8 over 2, which is 4 meters per second. And it's got a positive value because the gradient is in the positive direction. But how can we find the instantaneous velocity at 2.5 seconds? Well, we can do two things. If we had a proper graph here, we could simply measure the gradient of this red line here by measuring the distance on the x-axis, the change in value on the x-axis, with the change in time. But this isn't going to be very accurate. So what we can do is we can use differentiation and find the derivative of x with respect to t. And that will give us another expression that will represent the velocity throughout time. So if I've got delta x over delta t, and just to recap for a second, to find the derivative of x with respect to t for an expression that looks like this, our derivative would look like this. Delta x over delta t is equal to n a t to the n minus 1. So we're going to have to do this with every single component in this expression here. So delta x over delta t is equal to, and this is t to the power of 1, so we move 1 to the front of the coefficient, and that's t to the 1 minus 1, which is 0. And any exponent to the power of 0 equals 1. And now we've got 2 times t to the power of 2 minus 1. So this works out to be minus 4 plus 4t. And if we were to draw a graph with this expression, we would have a velocity time graph that looks something like this. So negative 4, which means it crosses the vertical axis at negative 4, and the gradient will be 4, so it will go up like that. So this graph shows us that the velocity is increasing linearly with time. So all we need to do now is plug in this value, 2.5, into our new expression. This expression gives us the instantaneous velocity throughout time for this particle. So Vx is equal to minus 4 plus 4 times 2.5 seconds. That equals 6 meters per second, positive. And this makes sense. And this does actually make sense because the particle at a later time would have a higher velocity. And we can see this when we plot out our velocity, instantaneous velocity expression here. So at a later time, we have a higher velocity. So in this lesson, we're going to look at acceleration in terms of kinematics. When the velocity of a particle changes with time, the particle is said to be accelerating. So on the left-hand side here, we have a velocity time graph. And this red line here represents the velocity of a particle throughout time. Just like with average velocity and instantaneous velocity in the last lesson, we can also determine the average acceleration and the instantaneous acceleration on a velocity time graph. So the average acceleration of a particle is defined as the change in velocity divided by the time interval delta t during which that change occurs. So the average velocity along the x-axis is equal to the change in instantaneous velocity divided by the change in the time. And this is equal to the particle's final velocity along the x-axis minus the particle's initial velocity along the x-axis divided by the final time minus the initial time. And we can see these variables on our graph here. So the average velocity, which is a vector, is represented by this blue straight line here. And we're measuring the average velocity of a particle between point A and point B. So if we imagine point A is here and point B is here, and this is along a one-dimensional line. But as we can see from the red curve here, the particle's velocity actually changes over that time period, over the final time and the initial time. Initially, the particle's velocity is changing quite rapidly over time. Then when we reach this point here, the particle's velocity is not increasing over that time period. It stays constant, but then when we reach the final time, the velocity or the rate of change of velocity starts to increase again. And the gradient of this curve here represents the instantaneous acceleration at each point in time. Just like the instantaneous velocity in the previous lesson, if we shrink down our delta t, which is this value here, if we shrink down this delta t until it approaches 0, this average acceleration will be more representative of the acceleration at the point A here. So if we imagine point B is brought closer and closer to point A, our average acceleration will be more representative of the acceleration of the particle at point A. And as delta t approaches 0, the instantaneous acceleration becomes. So the instantaneous acceleration equals the limiting value of the ratio of delta v over delta t approaches 0. And we can also express this as the derivative of the velocity with respect to time. In other words, the gradient at any point on this red curve here. So on the velocity time graph here, we can see that the instantaneous acceleration of the particle from point A to point B is either positive, like it is here, or it's zero, like it is here. If we were to see a deceleration, our red curve would have a negative gradient, or in other words, a force acting on the particle. Say if that's our particle, and our particle is moving in this direction, a deceleration would be equivalent of some kind of force pushing back on the motion of this particle from A to B. And we'll find out in later lessons that force is proportional to the acceleration. It's really important to mention here that if the velocity of the particle, which is a vector, points in this direction, and the acceleration acting on this particle is in the opposite direction, then the particle will slow down, as we can see at this point here. So at this point, the acceleration is negative, which means it points from B to A. So this is a negative acceleration. If, on the other hand, our acceleration is pointing in the same direction as our velocity vector, then we can see that our particle's velocity will increase over time. Now, if we were to plot an acceleration time graph of this particle going from A to B, we might see something like this. So at Ti, our initial time, we have a steep gradient here, which tells us that our acceleration is fairly high. Then this gradient starts to reduce until the gradient is zero. So the gradient reduces like this until it reaches zero. Now for a short time it's zero, but then the gradient increases again. Therefore, the acceleration will also increase. So it looks something like this. The velocity of a particle moving along the x-axis varies in time according to the expression Vx is equal to 40 minus 5t squared, where the velocity is in meters per second and t is in seconds. Find A, the average acceleration in the time interval t equals 0 to t equals 2.0 seconds, and B, determine the instantaneous acceleration at time 2 seconds. So this is our plot of the expression here. And you can see we have the zero line here, and at time equals 0, our velocity is 40 meters per second, and this is time. Our task is to find the average acceleration between 0 and 2 seconds. So in other words, we need to find the gradient of this line here, where this point is t final, and this point here is t initial. And we're going to make use of the average acceleration equation that we discussed previously, which is Ax is equal to the final velocity of the particle minus the initial velocity of the particle over the difference in time, which is t final minus t initial. But in order to find the final and initial velocities, we're going to need to use this expression here and insert the specified times into this equation. So let's do that first. So our final particle velocity is going to be equal to 40 minus 5 times the final time here, which is 2 seconds. And that's going to be squared. So 2 squared is 4, times 5 is 20, 40 minus 20 is equal to 20 meters per second, which we can see from the graph here. So we can either read off the graph or we can do it mathematically. The initial velocity, which should be 40, is equal to 40 minus 5 times 0 squared. And it's 0 because the initial time is at 0 seconds here. And this equals 40 meters per second. So we've got our final velocity and our initial velocity. We also got our final time and initial time, or the difference between the two. So our average acceleration along the x-axis is equal to 20 minus 40 divided by 2. And we get a negative average acceleration of minus 10 meters per second. Now we get a negative acceleration because the acceleration is a vector and the slope is negative here. So what about part B? It says determine the instantaneous acceleration at time equals 2 seconds. So what it's asking us is, what is the acceleration of this particle at this point here? So we can use differentiation to work this out. So we defined our instantaneous acceleration to be Ax is equal to the derivative of the velocity with respect to time. And as I've mentioned in a previous lesson, if we want to take the derivative with respect to time for this equation up here, we would do so for each component of this expression. So we've got, so Vx is equal to 40 t to the power of 0. And it's t to the power of 0 because that equals 1. So it's effectively saying, effectively what we're saying is 40 multiplied by 1, which is 40, minus 5t squared. So for each component here, we take the power and move it to the front, and then minus the power by 1. So we've got 0 times 40 t to the power of minus 1 minus 2 times 5 t squared minus 1. And this equals 0 minus 10 t to the power of 1, which equals 10t. So now with our instantaneous acceleration, we can insert the value of time equals 2 seconds into this expression here. So we get Ax is equal to 10 minus 10 times 2, which equals minus 20 meters per second. And there's something really important I need to note here. Because this acceleration is negative and the velocity at this point is positive, we have a situation where we have a particle moving in the positive x direction with a positive velocity, but then we've got a negative acceleration pushing back on the particle. So when you have a positive velocity with a negative acceleration working on that particle, the particle will slow down. And you can see this here. As we move forward in time, the particle's speed reduces until we hit around 2.8 seconds, in which the particle's motion reverses because its velocity is negative. But we still have a negative acceleration working on this particle. So it causes the particle to speed up in the negative direction. And you can see this here. So at 4 seconds, the particle is moving at minus 40 meters per second, and it will continue to speed up. In this lesson, we're going to focus on the equations of motion for one-dimensional kinematics. And I'm also going to show you what each term within the equation means and how to derive them. In the next lesson, we're going to use these equations to answer questions. I met a friend the other day who has done a maths degree, and he showed me how to derive these equations using calculus. And he started off with this expression here. And this means the second derivative of the position with respect to time equals the acceleration. And the acceleration does not change throughout time. And from this starting point, he was able to derive all these equations here. Now, in this lesson, I'm going to take a more basic approach to deriving these equations. And we're going to do so by looking at the position, velocity and acceleration time graphs to get our final result here. So let me first explain what all these terms mean. So imagine we've got a drag race where our track is about 400 meters long, and we've got a car at the start of the race at 0 meters at rest. Something like that. Now our race cars here can only move in one dimension. They're just going down a straight track. And we'll call this direction the x direction. Now initially, our race car is at position xi, which means the initial position. The car's final position will be at xf at the end of the race. Its initial velocity will be represented by vxi here, vxi, which would be 0 meters per second because it's not moving, it's at rest. Its final velocity would have some quantity that's above 0 meters per second in this case. So in this situation, we don't know what the final velocity is. And in this model, we're going to assume that the acceleration along the x-axis does not change over time. And let's call this acceleration 8 meters per second squared. Now you could have a situation where you're measuring a deceleration. So say if this drag car is moving at 50 meters per second and it's slowing down at a constant rate of minus 8 meters per second squared. The initial velocity would be 50 meters per second, 50, and we'll keep the initial position at 0 meters. Its final velocity, when it finally comes to rest, would be 0 meters per second, but we would not know the final position. We would not know how far the race car is going to travel to stop from 50 meters per second at a deceleration of minus 8 meters per second. So we don't know that answer there. But we can use all these equations above, or a combination of these equations, to find this answer. Now, these equations of motion will only work in situations where the acceleration does not change over time. So when we have an acceleration time graph with a constant acceleration like this. So imagine you're an astronaut and you're in a rocket travelling up to orbit. You may be accelerating at a constant rate of around 30 meters per second squared during some part of the rocket burn. And this is equivalent to around 3 Gs. So in other words, you would experience a force on your body that's 3 times greater than the gravitational pull on you on the surface of the Earth. So you would feel 3 times heavier. So you might find that the initial acceleration from the launch pad would quickly increase up to about 3g, and then it will be constant for a certain amount of time. These equations of motion above will only work during this constant acceleration, during this time here. But it won't work at the start when the acceleration is changing, and it won't work if, for example, something goes wrong with the rocket and the top capsule is ejected suddenly away from the rocket. If the top capsule is ejected, if something goes wrong with the rocket here, then you would experience a sudden acceleration in a very short amount of time, like this. And then that acceleration may plateau, like that. But in this time period, when the acceleration is suddenly increasing over time, these equations won't be relevant. You can't use them there. But when the acceleration is constant, you can apply these equations. But these equations are actually quite useful because in a lot of situations, the acceleration is roughly constant over time. Now, in a previous lesson, we learnt that the average acceleration is equal to the change in velocity over the change in time. But we also discovered that the instantaneous acceleration is equal to the derivative of the velocity with respect to time, as the difference in time approaches 0, so as delta t approaches 0. But since our acceleration is constant here and doesn't change over time, our velocity time graph changes linearly over time. So the average velocity here is equivalent to the instantaneous velocity. Because if we were to measure the gradient of the velocity time graph using this expression here, where we have the final velocity up here, minus the initial velocity, change in velocity along the x-axis, divided by the change in time, we would get the gradient of the velocity time curve. But if we took the derivative of this equation of the velocity time here, we would get the same value as the average velocity. So what we can do here is substitute the instantaneous velocity into this equation, because they result in the same value when velocity is linear over time, we can set the initial time to be 0. And with this equation here, we can transpose it to make the final velocity the subject of the equation. So if we do that now, if we multiply both sides by the final time, we get AXTF is equal to the final velocity minus the initial velocity. If we add both sides by the initial velocity, we get Vxi plus AXTF is equal to the final velocity. This is the first equation in our list up here. So we've got the final velocity of a particle moving at constant acceleration, doesn't change over time, is equal to the initial velocity, whatever that may be. It could be 0. So we could be starting off at rest, or we could be measuring a particle when it's in motion. And we do this over a specified time period. So in other words, if we look at the graph here, what we're doing is we're saying, okay, what's this value up here, given this time here, knowing that the acceleration, in other words, the gradient here, is a constant value with an initial velocity of 0. And this equation here generates this straight line, because it's in the form of y equals mx plus c. Now there's another thing worth mentioning about the velocity time graph here that's really quite important. The average velocity of a particle along the x-axis can be represented by the initial velocity plus the final velocity divided by 2. So for example, if you're in a car on the highway and you're initially travelling at 10 meters per second, if you increase your speed to 20 meters per second, your average velocity over those two speeds would equal 15 meters per second. In other words, if this was 10 meters per second at some time, and this was 20 meters per second at a final time interval, your average speed would equal 15 here, which is halfway between the two. And this only works when you have a velocity that changes linearly with time. It doesn't curve up or curve down. But we also noticed in a previous lesson that the average velocity can also be represented by the final position of the particle minus its initial position divided by the time it takes to move between those two positions. In other words, the change in position over the change in time. So we can use these two equations here to derive another equation of motion up here. So from these two equations, we know that they equal one another. So we can say, from the top equation here, the initial velocity plus the final velocity divided by 2 is equal to this equation down here, which is the final position minus the initial position divided by the time. Now we need to transpose this expression here to make one of these terms the subject of the formula. We're going to choose the final position to be the subject of this formula here. So I'm going to multiply both sides of the equation by t. And then I'm going to add both sides of the equation by the initial position. So I've rearranged some of the terms here so that it looks very similar to the equation above, which is this equation here. So that's our second equation. To derive the next equation, we can substitute equation 1 into equation 2. So we can add the left-hand side of equation 1 into this term here, because we've got the final velocity up here. So we get the initial position plus half of the initial velocity plus this term up here, which is equal to the initial velocity again plus the acceleration along the x-axis over a specified time. And just a note here, this final time assumes that the initial time was 0. So in effect, this is saying over a change in time. Multiplied by t is equal to the final position of that particle. So all we need to do now is just expand out these brackets here, and we get half of the initial velocity multiplied by time, because we've got time outside the bracket here, plus half of the initial velocity multiplied by time again, plus half of the acceleration multiplied by the time squared. And that is equal to the final position. So half of this component here plus half of the same component equals 1 of that component. So we get initial position plus the velocity, initial velocity multiplied by time, plus half axt squared, which is equal to the final position, which is the same as this equation up here. For the last equation, we're going to rearrange equation 1 to make t the subject and then insert it into equation 2 here. So subtract both sides by the initial velocity and divide both sides by the constant acceleration. If we substitute this term here into equation 2 here, we bring the final position and put it over here, which is equal to the initial position plus half the initial velocity plus the final velocity multiplied by this term here. Final velocity minus initial velocity divided by the acceleration. Now we can simplify these brackets here by multiplying out. We get the final velocity squared, Vxi multiplied by Vxf minus Vxi multiplied by Vxf minus Vxi squared. These terms cancel. Resulting in the final position, which is equal to the initial position, plus the final velocity squared minus the initial velocity squared over 2 times the acceleration. And we can rearrange to make the final velocity the subject. multiplied by 2ax. And that's the final equation. Now, in a later video, I'll show you how to use these equations and solve example problems with these equations. Depending on the course you're doing, you might not necessarily need to derive these equations from scratch like this, but you will definitely need to memorize these equations to answer questions in kinematics. So the equations of motion we derived in the last lesson are where xi is the initial position of a particle, xf is the particle's final position, vxi is the particle's initial velocity, vxf is the particle's final velocity, ax is the constant acceleration of that particle along the x-axis, and t is the difference in time between the final and the initial positions or velocities of that particle. So effectively, it's delta t, change in time. And just a reminder, these equations can only work when the acceleration is constant over time. Okay, so problem 1. A car is driving along a straight highway at 30 meters per second. This is about 70 miles per hour. The driver sees a truck that has jackknifed and is now stationary at 150 meters ahead. The driver instantly hits the brakes and decelerates at a constant rate of minus 4 meters per second squared. Does the car collide with the truck? So in order to begin answering this question, it's a good idea to draw a diagram of what we have. So let's imagine we've got a straight path where our initial position here, xi, is the position where the driver starts to brake. And we can assign that initial position with a value of 0 meters. Our final position, xf, is the stopping distance of the car while it decelerates at 4 meters per second squared. Now, we don't know what this position value is. We're hoping that it's less than 150 meters. But if this value is more than 150 meters where the truck is in relation to the car as it starts braking, then the car is going to smash into that truck. We know that our initial velocity is 30 meters per second. So we got Vxi is equal to 30 meters per second. We know that our deceleration as we start to brake, or in other words, our acceleration along the x-axis, and we'll call this the x-axis, is equal to minus 4.00 meters per second squared. And the negative sign here suggests that the acceleration, because it's a vector, is pointing in the opposite direction to the motion of the car. So the car is moving in this direction at the velocity of 30 meters per second, but the braking causes a deceleration of 4 meters per second, or in other words, an acceleration of negative 4 meters per second. We also know that our final velocity is going to be 0 meters per second because we want to come to a full stop long before we hit the truck. We know our initial position is equal to 0 meters per second. We don't know what our final position is yet. But with the information we have here, we can see what equation will fit our example problem. So we could choose one of these two equations here. We can also choose maybe this equation and simply transpose this equation to make xf the subject. But let's have a look at equations 2 and 3 first, because we might not need to do any rearranging. So we do have the initial velocity up here. We've got the final velocity up here, and the initial position, and the acceleration. What we don't have is the time. So we can't directly use equations 2 or 3 here at this moment. We could find the time using equation 1 and transpose it to make t the subject. And then, once we find the time, we could insert the time into this equation. And our time here would be the amount of time it takes for the car to come to a complete stop. But if we have a look at equation 4, all our variables here can fit neatly into the right-hand side here. So let's transpose equation 4 to make the final position the subject. And that should give us our answer. The final velocity minus the initial velocity squared divided by 2 times the deceleration plus the initial position. And that will equal the final position. So all we need to do now is plug in these values. So we have 0 squared minus 30 meters per second squared divided by 2 times the acceleration. And remember, the acceleration is negative here because we're braking, we're slowing down, plus the initial position, and we've set that to 0. 30 squared is 900 divided by minus 8 meters per second squared is equal to 112.5 meters. So the truck was 150 meters ahead and our car was able to stop within 112.5 meters. So it won't hit the truck. A bullet is fired from a rifle whose barrel length is 0.8 meters. If the bullet leaves the muzzle at 1200 meters per second, what acceleration does the bullet experience in the barrel, assuming the acceleration is constant? So imagine this is our barrel. The initial position of the bullet can be at 0 meters, and its final position, when it leaves the barrel, will be at 0.8 meters. Its initial velocity is going to be 0. It's going to be at rest. We're given its final velocity as it exits the barrel at 1200 meters per second. We do not know the acceleration and we don't know the time it takes for the bullet to travel down the length of the barrel. So if we look at our equations again, what equation most closely matches the variables that we have in our problem here? We're looking for the acceleration. We have the initial and final velocity and the initial and final position. And let's have a look at equation 4. So we can transpose equation 4 to make acceleration the subject. So let's do that. So our final velocity is 1200 meters per second squared, which is equal to the initial velocity, which is 0, plus 2 times whatever acceleration we have, multiplied by the length of the barrel, which is 0.8 meters. So 1200 squared is 1.44 million, which is equal to 1.6 times the acceleration. So the acceleration is equal to 1.44 times 10 to the power of 6 divided by 1.6. And that gives us 900,000 meters per second squared. So given the acceleration, can we work out the time that the bullet spent within the barrel? So given these four terms here, we can use equation 1. Because we got the velocities, we have the acceleration now, and all we need to do is transpose this equation to make time the subject. Because the initial velocity is 0, we can ignore this variable here, and we can simply say the final velocity divided by the acceleration along the x-axis, the constant acceleration, is equal to the time. So our final velocity is 1200 meters per second, 1200. Our acceleration is 9 times 10 to the power of 5 meters per second squared. And therefore, our time is 1.3 recurring times 10 to the minus 3 seconds. So in problem 3, we have a motorcyclist that is speeding and sees a speed camera 30 meters ahead. The cyclist manages to slow his bike down to 12 meters per second in 1.8 seconds, just as he passes the speed camera. What was his original speed? So in this situation, we have a guy on a motorbike. We don't know what his initial speed was, and that's what we're trying to find out. But his final speed is 12 meters per second. We can set his initial position at 0 meters, and that's the time when he starts to decelerate when he sees the speed camera. Now he traverses this 30 meters in 1.8 seconds. So the difference in time is 1.8 seconds. Which of these equations above could help us answer our question? Well, we're looking for the initial velocity. We've got the final velocity. We've got time. We've got the initial and final positions. We don't have the acceleration. So equation 1 and equation 4 might not be the best equations to use in this example. And also equation 3 as well. So maybe we can answer our question with equation 2, as all we need to do is transpose this equation to make the initial velocity the subject here. So let's try and do that. So the final position minus the initial position multiplied by 2 divided by the time is equal to the initial velocity plus the final velocity. We subtract the final velocity from both sides of the equation, which gives 2 multiplied by the distance travelled minus the final velocity, and this term here is divided by the time. So that's our equation. So we end up with 2 multiplied by 30 meters divided by 1.8 seconds minus 12 meters per second. And that gives us a value of 21.3 meters per second recurring, which is about 50 miles per hour.